Welcome back, AP Chemistry students, to Unit 9. Today we will be talking about Unit 9.4, Cell Potential. When constructing a galvanic cell, you've created a battery, and we measure how much energy your battery puts out as its voltage. Now, the technical term for a battery's voltage is its cell potential, designated by the variable E cell, sometimes referred to as the electromotive force. It's the measure of how much attraction electrons have for the cathode. It's the pull of electrons towards that cathode. So the voltage of a battery is how much energy those electrical charges of an electron can put out. So in your voltaic cell diagrams, you'll see that open switch. That's where we would leave a voltmeter to measure the voltage or the cell potential of your battery. Now, these cell potentials are based off of the standard reduction potentials of the electrodes involved, and they're standardized, meaning they're compared against something. Standard reduction potentials are compared against a hydrogen cell. How readily do hydrogen ions reduce into hydrogen gas? That we denote as having zero cell potential. And then everything else is compared to that at standard conditions. And again, those standard conditions is 1 atmosphere, 1 molar solutions, and at a comfortable 25 degrees Celsius. So when we talk about standard cell potential, or E naught, we denote it with E naught. So when you construct a voltaic cell, you're going to choose two metals that have different reduction potentials. Try to choose two that are cost effective, like for example in class, I'm not going to give you a gold battery. That would be insane, even though gold does have a fairly high reduction potential. And then we determine which element is going to reduce. The one with the most positive reduction potential is going to be the one that reduces and therefore is our cathode. And the one that has the lowest reduction potential is going to be our anode, because that is the element that would be easiest to oxidize, because remember, they run opposite. So on old versions of the AP exam, you were given this diagram, which shows the standard reduction potential of a vast quantity of substances. Nowadays, it's narrowed down, and for any free response or multiple choice, you'll be given only a handful, more likely specifically the ones you'll be working with. Notice that for some of them, they are based on elemental compounds, right? Elemental fluorine is readily reduced into fluorine gas, and others are based on ions. So we've said silver is always +1. Apparently silver can be +2, but that is easily reduced. Other elements are more difficult to reduce. Lithium ions are not going to readily reduce to lithium metal. More often, lithium metal is at a lower energy state when it's an ion, so its reduction potential is not very high. It's more likely to be oxidized. Lithium is more likely to be oxidized. So while this is a standard reduction potential, if you were to flip the sign of everybody, it could be the standard oxidation potentials. So to calculate the electromagnetic force, or E cell, of a particular battery, we're going to first determine what the two half cells are. Then we will write the cell potential for each one. If it is the opposite of the table above, we'll flip the sign, we'll balance the reactions, add everything up, and that will give us our cell potential and hopefully the overall reaction for our galvanic cell. So in a battery produced from aluminum and magnesium, aluminum ions go from being aluminum ions to solid state aluminum. The only way that aluminum could form a solid is if it were to pick up electrons, specifically 3 electrons. Solid magnesium is going to form magnesium cations by giving up electrons. Now, since these reactions happen at the same time, they have to produce and absorb the same amount of electrons. So both half reactions have to have the same amount of electrons in them. So if I were to double my aluminum reaction, that would give me 6 electrons, and if I were to triple my magnesium reaction, that would give me 6 electrons, and the reaction would balance. So when this reaction transfers 6 electrons, what is the cell potential? Well, the cell potentials you take from the table above. So in the table above, aluminum becomes solid aluminum and has a cell potential of negative 1.66. Magnesium ions and electrons make solid magnesium and has a cell potential of negative 2.37. Cell potential is independent of stoichiometric coefficients, meaning even though we doubled this reaction and tripled the bottom one, that does not change the cell potential. What does change the cell potential is the fact that magnesium is less likely to be reduced than aluminum. So we are going to flip the sign, because here magnesium is being oxidized. So we need the oxidation potential of magnesium. So in order to determine the cell potential for the overall battery, just add everything up. 6 electrons cancel out, so 2 aluminum ions and 3 moles of magnesium make 2 moles of aluminum and 3 moles of magnesium ions, and that reaction has a standard cell potential of 0.71 volts. So with that being said, we are done calculating cell potentials. On page 15, I want you to calculate the cell potentials for each of the galvanic cells that you labeled, and use page 14 in your packet, which has the reactivity series for all of them. Also on page 16, rather than give you diagrams, I simply explain. We have voltaic cells with different electrodes. You are to determine which one is oxidized, which is reduced, calculate the cell potential when asked. Remember, the element with the more positive cell potential is the one that is going to be reduced and is therefore your cathode. The species with the more negative cell potential is the one that is going to be oxidized and is therefore your anode. So go ahead and complete page 15, do page 16, and again, use the cell potentials on page 14. Next class, we'll talk about what if you don't have 1 molar solutions at 25 degrees Celsius. What changes about your cell potential? I will see you then.